Alright, should be live. Cool. Alright, welcome to April. It's a very exciting day, or something like that. So, I'll let people get in here for a second. So I see no one in our Discord, but hopefully people are here. Can I get like a cap in the chat if you're paying attention? Nice. You'll love to see it. Okay, so the goal today is basically to leave feeling like cycle notation is super useful. Okay, so we talked a decent amount about SN, the symmetric group, back in our first chapter. It was kind of like the first group we really saw, right? And some of these results actually will come from the things we did back then. Basically, we said that SN can be generated by swaps, right? So SN can be generated by swaps. This is something we talked about way back, and now we have a better notion of like what a swap is, right? Before we use like this S12 notation, now we think of it as 1-2, and instead of the word swaps, we will now call these transpositions. And so basically this just means that anytime you have a permutation, right, you can write it as a product of disjoint cycles, but somehow we'll be able to break up these cycles into products of transpositions. And basically it's going to be the same arguments that we saw way back in our first couple of weeks. But before we get there, I just want to get more familiar with cycle notation and see why it's super useful. And one of the main reasons is it allows us to see what the order of a permutation is quite quickly. Okay, so let's get more used to what's going on. All right, so I think we left off at F-ish. I think we at least got through E. Maybe we said what F was, but we didn't talk about it. I don't think so. Right, this was the permutation sigma alpha. And so just to actually write this down, we had alpha is 1, 2, 3, 4, 5. Okay, right, so this guy's alpha, and then this guy altogether is sigma as a product of disjoint cycles. And so if we want to figure out what this is, right, you just kind of start going, and again, we're going right to left, right? So we have 1 goes to 2, all right, 2 goes to 5. So I'm just going to kind of belabor the point on the first couple just to really get used to it. And then 5 does nothing in the third one, so we're good. Okay, so 1 goes to 5. Well, then where does 5 go? So 5 goes to 1 in alpha, and then 2, 5, 4 does nothing to 1, and then 1 goes to 3. Okay, so then 3. So then what does 3 do? 3 goes to 4. 4 goes to 2. And then 1, 3 does nothing to 2, right? So this goes to 2. What the? There we go. I don't know why I already closed that off. It's because I know the answer, I suppose. Okay, so then 2 goes to 3. Yeah. And then 3 does nothing here, and then 3 goes to 1. And so 2 goes back to 1, and then you know that 4 is the only thing left over. It must go to itself. If you want to verify that, we absolutely can, right? So 4 goes to 5, and then 5 goes to 4, and then the last one does nothing to it. And so this is our end result. Okay? And just let me know if any of that didn't make sense. So the next one, right, so we have alpha and sigma up here. So there are two ways you can do this. So how do we get alpha inverse sigma inverse? There's a long way and there's a not so long way. We talked a little bit about how to get inverses last time. Socks and shoes seems like it could be useful. Yes, exactly. Yeah, so the long way would be like reverse alpha and reverse sigma and then like do what we just did for F. The quick way, exactly, is socks and shoes because this is the inverse of the thing above, right? This is sigma alpha inverse, and so we just reverse the order from this guy. And so you can just write 2, 3, 5, 1, and if you like your guy to start exactly with 1, then we have 1, 2, 3, 5. Good. Yeah, that is definitely the quick way to do things there. I like that. Okay. And then we had beta is 2, 4, 3. So then beta squared. And this is important because last time we noticed what happened when we multiplied alpha. Like a couple of times we saw that we were like adding. But here we don't have that like this goes to this plus 1 and this goes to this plus 1. But we're going to see a similar pattern. What do you guys think beta squared was? And did you see a pattern for what was going on? Yeah, it's 2, 3, 4. And the reason for this, right, is what's happening. Well, essentially, you're going 2 down the line, right? So this one, you just go 2 goes to the next, 4 goes to the next, 3 goes to the next, which, you have to cycle back around. This one says, okay, go to the next, but then that next goes to the next. So basically you're going 2 down the line, but it's not literally adding 2, it's going 2 down the line in the cycle, right? And so 2 goes to 3, 3 goes to 4 because this is 2 later, and then 4 goes back around to 2. Right, so maybe like another example. What if we saw, I'll just, I guess, make something up, like 1, 3, 5, 4, 2. And we wanted to see this squared, right? So that means 1 should jump to 5, 5 should jump to 2, 2 will go 1, 3, and then 3 will go to 4, and then 4 back to 1. Right, so you're just like jumping 2 in the cycle each time. And so this is 1, 5, 2, 3, 4. If you wanted to do cubed, right, so the first one sends it 1 over, second one sends it another 1 over, third one sends it a third 1 over, and so you're jumping 3, right? So like 1 goes to 4, 4 goes 1, 2, 3, 4 goes to 3, 3 goes 1, 2, 3 over to 2, 2 goes to 5, and then 5 goes back to 1. Right, and so this guy would be 1, 4, 3, 2, 5. Do we see that pattern, like what's going on there? Because that's very important for the proof of 484 when we're talking about the order of a cycle being how long it is. Does that seem to make sense? Cool. Good. Awesome. Yeah, so that's really the key step. So I'll just put like key for 484 here. Right, so this is why we kind of extended that argument. Okay, so then we should be able to figure this out pretty quickly. Beta cubed, well, beta is 243. We're just going around 3, but it's length 3. And so you're just going back to where you started, right? So this is going to be the identity. Okay. And then this next one will be the last one that I do like laboriously. And then we can, sigma cubed is an interesting one. Okay, so here again, if we just break it down, 1 goes to 2, does nothing to 2, 2 goes to 4, so 1 goes to 4, 2 goes to 3, but then 3 goes back to 2, so that does nothing. Wait, I don't know why I wasn't looking at 4. That's true. I'll put it down here. It's getting ahead of myself. Alright, 4 goes to 5, 5 goes to 1, this does nothing to 1, and so this is closed off, right? So 1 goes to 4, 4 goes to 1, 2 goes to itself, 3 goes to 4, does nothing, 4 goes to 3, 3 goes to itself, and then 5 must go to itself since it's the last one left, but we can also check, 5 goes to 1, 1 goes to 5. So this guy is actually just a really long way to write a transposition. Okay? All right. So this one, again, sigma is 13254. So if I want to look at sigma cubed, how did you think about this? Did you actually multiply it out a whole bunch? Did you utilize a property that you know? How did you attack this? There's again kind of a quick way to do this. Something we talked about last time and I believe prove in 481. It's the same for beta cubed. 254 is the same for beta cubed. Right, but like why are we allowed to do that, right? Because ostensibly this looks like 13254, 13254, 13254. So the 254s aren't together, so you can't do 254 cubed, right? But why can we? What's the key? Yeah, they're disjoint. Exactly. So we know disjoint cycles commute. So disjoint. We kind of pointed that out last time, and you prove it in the next problem, but you can absolutely use it here. So this is really this guy. And basically, you know that 1, 3, and then 1, 3 is the identity, so this becomes just 1, 3, and this is E. And so you just get 1, 3. This again is just a transposition. Cool. And then what about this very last one? So what happens if we do sigma to the 6th? Well, if we know sigma cubed is this, it's this squared, and so that's got to be E. And this is our first little example, right? So something we're going to prove in a bit is that if you have a product of disjoint cycles, then the order is the LCM, the least common multiple, of the orders of the cycles. And so if you look at sigma, right, you've got a 2 cycle and a 3 cycle. And so you would look for the order to be the LCM of 2 and 3, which is 6, and this happens to be true. So we just showed the 6th power gets you the identity, and you know, if you wanted to do a little work, you could show that none of the previous powers were the identity. And it's exactly because they're disjoint, right? That basically the powers of each of these pieces have to get you to the identity, and so we know how that works, right? Like if it's order n, then if you have the kth power as the identity, then n divides k. And so you have something that divides both. So, 2 has to divide it, 3 has to divide it. Well, what's the smallest thing that's a multiple of both? The least common multiple. Okay. So 481 is, right, disjoint cycles commute. So like assume alpha and beta are disjoint cycles. Show alpha beta equals beta alpha. Why am I using the LCM of K and G? Well, I'll prove it rigorously in 485, but yeah, the idea is basically that sigma to the K is going to be 1,3 to the K times 254 also to the K. And so if this is equal to E, well, basically the fact that these affect different pieces means that these both have to be E simultaneously. And so this means that K is divisible by the order of 1, 3, so 2 divides K, and it's divisible by the order of 2, 5, 4, so 3 divides K. And so basically K is a multiple of both. The order is the smallest one that does this, so you want the least common multiple. So with the disjoint cycles commuting, I imagine that you can kind of just see it. You could kind of explain it in words. I wanted to give you just kind of like an alternate path just to kind of have you thinking about permutations in different ways, because a lot of times you're just thinking like, oh, it's this cycle or whatever. But if you think back to our definition, right, the definition of a permutation is as a function, right? So permutation of x is a one-to-one onto function from x to itself, right? So how is this useful for disjoint? Well, that means basically we can write x as like the union of two disjoint sets, right? So it's the union of these where their intersection is the empty set. So basically you just have two pieces, right? So you've got like, this is my u, and this is my v, and then the whole thing is x. So I've just kind of split it into two pieces. And basically you're just viewing alpha. I mean, sure, it's from x to x, but really you can view it as fixing the things in v, not affecting them. So view it as alpha from u to u, right? Alpha only affects this part. So alpha does something to these three guys. And then beta, you would view from v to v, right? So like beta would deal with these two guys. And so then if you look at what happens when you actually do the function, right? So alpha beta of x is equal to, well, if x is in u, then beta fixes x, right? So beta of x equals x if x is in u. And so you just get x, and then you get alpha of x, whatever that does, because alpha actually does things to things in u. And then similarly, if x is in v, well, beta does something to it, and then alpha will fix it, because alpha doesn't affect the stuff in v. Well, what if we did it the other way? You're going to get the same thing, right? Because, again, if it's in u, alpha affects it, but then beta fixes it. And so I just get alpha of x back. And if x is in v, then alpha fixes it, so I get x, and then I plug x into beta, so I get beta of x. Well, these are the same, right? They're the same on every point. So alpha beta equals beta alpha as functions. Okay, so this would be just kind of a very rigorous, well, I say very, I mean, I say view it as this. I mean, if I was being very rigorous, I would say that alpha of x equals x for all x in v. But But yeah, that's basically what I mean by view it as this. So this is a mostly rigorous way to think of this, and really using the definition. I just kind of wanted to like view it from another perspective. But you can kind of eyeball it and have the intuition of like, okay, this only affects this only affects this. They don't mess with each other, so it doesn't matter in which order I do them. And that's true. Okay. All right. So what did we get for the orders of elements? So now this is our goal, right? Our goal is to really show what the order of elements are inside Sn. So what are the orders of elements in S3? So last time we said that we have, I guess it doesn't matter which order I write them in, these 6 elements. What are their orders? Or like maybe you can group them into a few families and not do them one by one. What did you notice when you were looking at order? Order is the size of the set inside the parentheses. Yeah, it's just the length of the cycle, right? So basically order of E is 1, order of 1, 2 is the same as the order of 2, 3. That looks like 2, 1, 3 because I can't write. 2, 3 equals the order of 1, 3 is 2, and then the 2, 3 cycles have order 3. Yep. Okay. I agree. It is as simple as that. And I mean, you can either do it out. We kind of noticed this above when dealing with powers of things. And obviously, the transpositions are very easy because it's just like switch back. The longer cycles, you just kind of have to notice the pattern after a little bit of practice, and you can see why this is going to be true. Or you can compute it out. So then I wanted you, just because we hadn't really seen this, you can't really do interesting disjoint cycles inside S3, right? Because the only disjoint cycles, you're going to have one of size 1, which is just do nothing. So went up to S4 and said, think about 1, 2, 3, 4 in S4. So what's the order of this guy? Toss me a number here. Okay, yeah, so that's a good thought, right? It might be 4, because we saw earlier, right, that the order of that sigma, which was, let me look back, 1, 3, 2, 5, 4. We saw this was 6, and so it kind of looked like, hey, order 2 times order 3 means I get order 6, so maybe in general the order of the product of disjoint cycles is just the product of the orders. But, yeah, so it ends up being 2, which kind of dispels that notion, right? So like your first conjecture might be the order of a product of disjoint cycles. I can save this. Nice. Is the product of the product of the orders. So no, this is a counterexample. No, this 1, 2, 3, 4 is a counterexample. And the reason that it's order 2, right? So again, they're disjoint. So 1, 2, 3, 4 squared is 1, 2 squared, 3, 4 squared, because they commute. And so we can like just put them, we can gather all of our 1, 2s, we can gather all of our 3, 4s, and this is going to be the identity because each of them are order 2. Right? So to the fourth power also gives you the identity, it's just not the smallest one. And so this is where you might conjecture, like a revised conjecture would be that the order is the LCM of the product of the orders, not the product. Basically that like if they share a common factor that somehow that matters, right? That they don't have to travel around the same amount. So we're going to get into how to actually prove that here in a second. So any questions first before we dig into like proving first that the length of a cycle is actually its order? And I mean, I wanted to point out here, right, like this is how math works, right? Like you just make a conjecture from a couple of examples, like, oh, okay, like I saw this seems like it's the product, and then you just check out another example or try to prove it in general, and you see, oh, okay, like that fails. Okay, well, do I still see some sort of pattern? All right, I'll revise my conjecture. Maybe it's this instead, and then, you know, like this is just how mathematics is done. Okay, so let's go ahead and prove, this is what, 484, that if alpha is a cycle of length k, then the order of alpha is k. Okay. So this pretty much relies on some sort of induction argument, because you want to figure out like what the powers are, right? So like again, showing the order equals something involves two things, right? So like one, you have to show that alpha to the k is actually the identity, and then two, that k is the smallest positive power such that this is true. Such that and so like this isn't as easy as it looks. I mean, we can see it from that example. You can like see the pattern. The question is, do you see how to rigorously state what pattern is going on, right? So again, let's maybe look at this guy. I'm just gonna throw this out here. So the point is, right, like this moves everything over to inside the cycle, right? So this is going to be 1, 4, 2, 3, 5, right? And that like another power would take it down another 1, and so down 3 from your original. So what's really going on? Can you tell me in general? So like if I write 1, 3, 4, 5, 2 to some power in general, so say to the mth power, can you tell me where 1 goes? So we said like the second power, right, you're going to go 2 over. Third power, you go 3 over. Fourth power, you go 4 over. So where should this go? It will move a distance of m. Yeah, so it goes m over, but this is mod 5, right? Because like, what does it mean to go 8 over? Well, there aren't 8 things, so it really just means like it went 1, 2, 3, 4, back 5 to its original, which is like 0, mod 5, 1, 2, 3. So it would end up being here. So like if m equals 8, 1 goes to 5, because really it's like going 3 over. Okay, so what you want to show then is, let's write alpha in general, right? So alpha is, I don't know what these are, right? I don't know in what order they're written. So I'm just going to write it as alpha 1 down to alpha k. Yeah, exactly. Yeah, this mod 5 business. So I have my k elements in my cycle. And so my claim here, now I can really be specific, right? Because I say like it goes m over. But now I can really say like what that means, right? So alpha 1 here goes to alpha, well, what does it mean to go over m? Well, I'm adding to the subscript, right? So this goes to alpha 1 plus m mod k, right? Alpha 2, it goes over m, so it goes 2 plus m, but again, mod k, and so on. Ah. So does that make sense how I'm writing that? So I've tried to make it in this like more general context, right? But it's the same business. This is exactly moving over m, but we're doing it mod k because we know we have to cycle back around. Let me know if you want clarification on that. So in general here, if you actually wanted to prove this rigorously, which I'm not quite going to do here, this might be a problem set thing where I have you actually write it up super nicely, but to prove this rigorously, you would use induction on m. Right, so basically your base case would be what happens when you square it, you see that it goes over, or well, I mean you could honestly just do to the first power, but then, yeah, essentially seeing what happens when you multiply 2 of them and that it goes over 1 from the previous is like your induction step, okay? And so basically the fact that every time you multiply, you push it over 1 is exactly why you get up here. And so that kind of naturally lends itself toward induction on m. Okay, so the question is, when is this the identity, right? So let's actually verify 1, so we want the alpha to the k equals e. Well, alpha to the k gives us alpha 1 goes to alpha 1 plus k mod k. And in general, right, because these are all the same, alpha I goes to alpha I plus k mod k. But what is I plus k mod k? Yeah, it's just I mod k, right? Because the k is divisible by k. So this is just I mod k. Oh, but that is just I, right? Because I is less than k. And so that means that alpha I goes to alpha I. Well, that means all of them are fixed. So that means alpha to the k is the identity, right? The permutation which fixes everything is the identity. Okay, so that's the first part. So then, why is k the smallest? Smallest such power. Well, you would need alpha I is equal to alpha I plus m mod k for all I, right? If we fix everything to be the identity, right? So basically this is like alpha to the m equals e, then this would be true. Well, if I plus m is equivalent to I mod k, what does this mean must be true of m? If I plus m is equivalent to I mod k, what must be true about m? K equals m. Yeah, so it need not be equal. It's a multiple of k. Yeah. Then m equals, sure, nk for some n and z. Basically, we get that k divides n, right? That's what that means. And so, in either case, k is less than or equal to m, right? And so k is the smallest, so the order of alpha is equal to k. Yeah, Eddie, so that would also be true. M is 0 mod k, right? Not necessarily 0 itself, but 0 mod k, and that is exactly being divisible by k. So, yes, that's another way to phrase it. Cool. So hopefully that makes sense. So it's basically, right, like, you notice the pattern pretty quickly. It's just a matter of how do we phrase this rigorously, right? And so we need modular arithmetic there, and then we're just kind of applying what we know about modular arithmetic and divisibility. Okay. So then, to show the order of a disjoint or a product of disjoint cycles is the LCM is a little harder. So again, like, this is hopefully a conjecture that comes from looking at a few examples. We seem to think it's true. The question is, like, how do we prove it? And again, we've kind of noticed what the key is. So let me start by just like getting the notation down. So it was what, m disjoint cycles? Yeah. Okay. So let alpha equal alpha 1 pose. I'll write the composition just to make it clear, like, this is very different than what I wrote above, right? Like, this is not a cycle here. Each of these guys are disjoint cycles. So, like, this is the composition of permutations, where each alpha I is a cycle of length k sub I, right? Because they may be different lengths, and so it depends on the I, so you kind of have to have a subscript there, and they are all disjoint. So we've written it as some product of disjoint cycles, and we can always do this, right? This is always possible for any permutation, and so that's why this is so useful. Like, we're really getting the order of any permutation here. Okay, so after that, yeah, so I guess more shorthand, I can write this. Then the point, right, is that if I write alpha to the k in general, some power k, then yeah, it's really like all of these to the k, you do it over and over, but because they're disjoint, right, you can actually gather them all together and get each one to the k itself. Right, so since disjoint cycles commute. So this is why disjoint cycles commuting is so important, right? That you can gather them together and really look at their powers individually. And so basically, if alpha to the k is e, then my claim is alpha to the I to the k must be e for all I. Why is this true? Because in general, this is not true, right? That if you have a product of a bunch of things that equals the identity, it does not mean that each thing is the identity, right? So for instance, like r cubed is the identity, but r cubed is r times r times r. Well, none of these are the identity, right? In R3. So like, this is definitely not true in general, but like, why is it true here? Why, in this specific case, does it happen? So I'll just put not true in general. Because they're disjoint cycles. Exactly. So like, you can have things that multiply together and give you the identity, but you can't do it if they're disjoint, right? So since the alpha I are disjoint, so are the alpha I to the k, right? So like alpha I only affects this little group. Well, then powers of alpha I still only affect that little group, right? They don't suddenly jump out and affect other things because you're still just applying alpha I each time. So basically, you have a bunch of disjoint things giving you the identity. Well, there's no way they interact with one another, so they couldn't like somehow be inverses of one another, right? And that's the key. There's no way they interact with each other to get the identity, so each piece had to be the identity from the start. So this is crucial because what does this tell us? So since alpha I to the k equals e, what do we know? Because remember, we're given the order of alpha I. So what must be true here? What can we conclude? So the kth power gives us the identity, it's order ki. What must be true? Remember our stuff from the cyclic groups section here about order. If you know the order and you see a power of something goes to the identity, what must be true? This was like 424 or something like that, I think. I'm seeing no responses. It's finite. It is definitely finite, but we can say a lot more. There's some relation between ki and k. I mean, it's the order, so it's definitely the small k to the I equals in k. It's the other way around. Yeah, exactly. Perpetually confused. Yeah, so ki divides k. Right, the order divides any power that takes you, positive power that takes you the identity. I guess negative powers too. Okay, so this is true individually, but it's true for any of these i's, right? I was arbitrary here. So ki divides k for all I. Equivalently, right, we can think of this as meaning k is a multiple of ki for all I. If alpha to the k equals e. So, if you want the smallest power, right, if we want k to be the smallest power, what must be true? Well, we know it has to be a multiple of all of them. You want the smallest multiple. That's exactly the definition of the LCM, right? Smallest such power, it must be the smallest or least common multiple of the ki's. Multiple. So the order of alpha is equal to the LCM of, of the ki's. Does that make sense? Questions on that? So basically you just see what happened. You're right, we use the fact that it's a disjoint to rewrite it with powers of each of the alpha i's individually. We realize that for the product to be the identity, since they're disjoint, each piece must be the identity. Well, if you have a power of something that goes to the identity, that power must be a multiple of the order, right? So now k is a multiple of ki for all of them. We want the smallest one that's going to get us the identity. So we have the smallest multiple of all of them, the LCM. Okay. Well, a natural question after that, right, would be, well, we use disjoint there. Is this true? If cycles are not disjoint. Okay, I see a no. Do we have a counterexample? So I agree. $479A. You're gonna make me work, huh? Okay, yeah, that would work. So basically, you're saying 1, 2, 3, 4, 5 times 1, 5, which was 2, 3, 4, 5. So this would be 5 times 2, which is definitely not equal to 4. Yeah, so how would I find a counterexample? So, right, I mean, I just want to look for essentially cycles that are not disjoint and then figure out the order. So kind of a smaller one, if you just do these two together. So this is exactly 1, 2, 3, right? 1 isn't affected, it goes to 2. 2 goes to 3, doesn't change. And then 3 goes to 2, which goes to 1. And so this is 1, 2, 3. And yeah, you just basically cook up an example and see what happens, right? I don't think there's necessarily like a ton of intuition that goes in before. You just kind of have to play around a bit until you're comfortable with Sn. And here, of course, this is order 3. These are each order 2, and 4 is not 3. And in fact, this will, yeah, pretty much any example that you come up with of non-disjoint cycles, you're going to get a counterexample. Okay, so then, yeah, this was just kind of practice, right? And if you want more practice with LCMs, I mean, you can just come up with them yourself really easily, right? Like just create any whatever cycle you want, do the LCM of stuff, and these are pretty easy to come up with examples for. So here, just did like a 3 cycle, a transposition, and a 4 cycle. So then if I call this, alpha, then my order of alpha is the LCM of 3, 2, and 4. What is that LCM? Right, it's 12. Okay. And really that's because of 3 and 4, right, more than anything. that is the LCM of those two individually. So where we're going to kind of go moving forward, so there's a little bit of stuff on these Cayley graphs. I think 489, just quickly. Now, your picture may vary a little bit, but if you use 1, 2, and 1, 2, 3 as your generating set, you should think of this as looking a lot like D3. We know they're isomorphic, right? And this is kind of your R, right? It's an order 3 thing. This is your order 2 thing. And so this is the one that's like the triangle within the triangle, right? So this is your S's are your double edges, and then, you know, you go around in opposite ways on the two triangles. So like this is like E 1 2. This is like 1 2 3 1 3 2. I think this is 1 3 then, and this is 2 3. But we're next going to basically go back to what we did in chapter 2 a little bit and look at breaking down cycles into transpositions. So basically, like what I did here, once you think a little bit more about this and think about how to break things down into transpositions, one, it's always possible. You can always write any cycle as a product of transpositions. Even more specifically, you can write it as a product of adjacent transpositions, basically things that look like this, right? 1, 2. 1 and 2 are next to each other. They're adjacent. 2 and 3 are next to each other. If I had written this as 1, 3 times something, those would not be, like 1, 3 is not an adjacent transposition. And so basically this will get back to like basically just using cycle notation to do the work we did before when we showed that symmetric groups are generated by swaps. Okay, so we won't spend a ton of time on that, but we'll spend a little bit, and then I'll probably talk some about the alternating group and Cayley's theorem, which are important, but probably not things we'll spend a ton of time on before moving into normal subgroups and cosets and start getting ready for quotient groups. Basically, our way of like division of groups. Okay, so that's the plan going forward. If you guys have questions, right? So we have a problem set due Friday. I'll be around this afternoon. I'll also be around for a few minutes here after class. So feel free to ask those. Otherwise, have a delightful afternoon.